This is Vamsi Mohan, Dr. U. Vamsi Mohan, Professor of Civil Engineering, Institute of Aeronautical Engineering. So I am dealing with the course Strength of Materials, and today's topic is about the theory of bending, the assumptions made in the theory of simple bending, and the derivation of bending equation. In theory of simple bending of beams, we make some assumptions for simplification of understanding. So here we are going to study about the bending behavior of beams and the relation between various parameters such as moment of inertia, Young's modulus, the curvature of the bending curve, etc. So the beam, which is initially horizontal, is assumed to be straight. That is the first assumption, and is unstressed. So we can consider a simply supported beam or a cantilever beam subjected to some sort of loading. So in simply supported beam, the bending of beam will be something like this, with top fibers being compressed and bottom fibers being elongated. Okay, so it is under tension. Bottom portion is under tension in simply supported beam, and top portion is under compression. Whereas in cantilever beam, the bending of beam will be something like this under the action of external loads. And in this case, the bottom fibers will be under compression and top fibers will be under tension. Top fibers will be under tension. So the nature of stress changes from tension to compression. It means at some point in between, there lies a layer which is neither compressed nor subjected to tension. Okay, and that layer is called neutral layer. That means it changes sign. The stresses changes sign from compression to tension. It means it becomes zero at some point. Okay, that is called the neutral layer, at which this layer is called neutral layer, at which the compression and tension layers they at which actually there will be no tension at neutral layer, or no compression, no stresses at neutral layer. Okay, and the cross section generally we will assume here a rectangle. It may be any other shape also. So the neutral layer, the line of intersection of neutral layer with cross section is said to be neutral axis, which passes through the centroid of this cross sectional area. Okay, the neutral axis passes through the centroid of the cross section of the beam. Okay, so the first assumption in the theory of simple bending is the beam is initially assumed straight and is unstressed. And the second assumption is the material of the beam is perfectly homogeneous and isotropic, that is, of the same density and elastic properties throughout the beam along the length of the beam. Next assumption is the elastic limit is nowhere exceeded. It means the stresses are within the elastic limit. That is, it follows Hooke's law. And fourth assumption, the Young's modulus of the material of the beam is same in both tension and compression. Young's modulus E is same in tension as well as in compression. That is another assumption. And here plane sections remain plane before and after load application, after bending and before bending. The plane sections remain plane. The cross section, which is plane before bending, remains plane even after bending also. That is another assumption. And next assumption is every cross section of the beam is symmetrical about the plane of bending. Symmetrical about the plane of bending. That is about an axis perpendicular to the neutral axis. And there is no resultant force perpendicular to any cross section. So the forces are assumed to be transverse in beams. Okay, that means the forces are perpendicular to the axis of the beam, and there is no force which is resultant force on the cross section. That means perpendicular to the cross section. So it means the stresses, the forces are perpendicular to the axis of the member. So these are the assumptions made in this theory of simple bending. So with these assumptions, we'll proceed to derive the equation of simple bending. So for that, let us consider a beam which is initially unstressed and subjected to a constant bending moment along its length. That is pure bending. The case of pure bending is an assumption actually. Yeah, we can see an example for this. The case of pure bending. Yeah, in this case, the portion of the beam between CD is subjected to constant bending moment. That is only pure bending moment. Shear force is 0 between C and D. Okay. Pure bending means shear is 0. It is clear. So the shear force diagram, if you draw, it will be something like this. Okay. Shear force diagram for this beam. So the theory of bending, we assume pure bending case. Okay. So the equation is derived based on the assumption of pure bending only. Okay. And it is assumed that the bending curve is circular in shape. The bending curve is circular in shape. That means the radius of curvature is constant. The radius of curvature is constant. As a result of this, the bending, the top fibers of the beam will be subjected to tension. And that is in case of cantilever. we have seen the top fibers are compressed, the top fibers are subjected to tension and bottom fibers are subjected to compression. In simply supported beam, it is opposite. The top fibers are subjected to compression and bottom fibers are subjected to tension. And we have seen what is neutral axis actually. It is the line of intersection of the neutral layer with the cross section of the beam. It may be of any shape. The centroid of the cross section, the neutral axis passes through the centroid of the cross section. Okay, let us consider the case of cantilever beam, in which the top fibers are subjected to tension. Okay, so we consider a small portion of this. Okay, small portion of this cantilever beam of length dx. Okay, so first part A, the figure A shows the unstressed beam, and figure B shows after the application of load, after bending the beam, the portion of beam is shown in figure B. And here it is assumed that the radius of the curve is R, capital R. Okay, and the angle subtended by this portion at the center of the curve is theta. Yeah, with reference to this figure, so we consider the cross section of beam HE and GF, two cross sections separated by a distance dx. Okay, let us come back to this figure. HE is one cross section and GF is another cross section separated by a small distance delta x. Okay, and here CD lies on neutral axis. That means the length of CD remains same even after the bending has taken place. Okay, so the CD being on neutral axis, neutral layer, it will not be subjected to any stresses. So its length remains same before and after bending. Okay, before bending its length is delta x, and the same length it will have after bending also. That means C dash D dash, the length C dash D dash is equal to CD. The length remains same for the neutral layer CD between the cross sections considered. And we consider another layer AB at a distance y from the neutral axis. Another layer AB above the neutral axis at a distance y. So A dash B dash is the length of this after bending. So what happens is all the layers above the neutral layer are elongated. That means the length increases for layers lying above the neutral layer. And for layers lying below the neutral layer, the length decreases because the layers below neutral layer are compressed. For example, if you consider EF, the length of EF is greater than E dash F dash because E dash F dash is compressed. Similarly, HG, the length HG is greater than HG is less than H dash G dash. H dash G dash is elongated length of layer hedged. Similarly, A dash AB is also less than A dash B dash because it is elongated. Being above neutral layer, the layer AB is elongated. Okay. Consider two layers now. Consider some fiber AB. We have considered some fiber AB at a distance y above neutral layer. This is neutral layer, and we are considering layer AB at a distance y. So A dash B dash is the length after bending. Okay, A dash B dash is the length of layer after bending. This is neutral layer C dash D dash. So A dash B dash minus AB is the extension. A dash B dash is the final length. AB is the initial length. So the difference of this is the extension of the layer. Okay. So original length is AB and extension is A dash B dash minus AB. So the strain the layer AB undergoes is equal to extension divided by original length. That is A dash B dash minus AB divided by AB is the strain to which the layer AB is subjected. And in this case, AB is equal to CD. Initially, in unstressed condition, AB is equal to CD. Okay? And CD is equal to C dash D dash. Because it is unstressed, the layer CD is unstressed, its length before and after bending remains same. Okay? So, consider the fiber AB, and the strain in the fiber AB is now is given as extension of the fiber AB divided by original length. So A dash B dash minus AB is the extension and AB is the original length, initial length. So extension is given by this expression. Okay. Yeah. So strain is given as A dash B dash minus C dash D dash divided by C dash D dash, because AB is equal to CD, which is equal to C dash D dash. Okay. And what is A dash B dash? In terms of radius r of the curve and theta subtended at the center. Okay. So what is A dash B dash? Let us see now. It is A dash B dash. Let this be the center O. This is C dash D dash. From C dash D dash to O, that is C dash to O is radius. So the strain in fiber AB is extension divided by original length. We know that. So the extension of the fiber AB is A dash B dash, the final length minus initial length AB, divided by initial length or original length AB. Here AB is equal to CD. We know that from the unstressed condition, AB is equal to CD, and that is equal to C dash D dash. Okay, CD is equal to C dash D dash. So here, replacing AB by C dash D dash, we will have the expression for strain as A dash B dash minus C dash D dash divided by C dash D dash. And the observing this figure B, the angle subtended by the portion C dash D dash at the center is theta, and the radius of the curve to the neutral layer is r. So the length of c dash d dash is equal to r theta, theta being in radians, and the length of a dash b dash, which is at a distance of y from neutral layer. So total radial distance is to a dash, it is r plus y into theta. Okay, so the length a dash b dash is r plus y theta minus c dash d dash r theta divided by r theta. Okay, and that is simplified as y by r, because r theta cancels, y theta by r theta, that is y by r. So this is the strain equation, and we know that the stress by strain is given as Young's modulus. The stress by strain is given as Young's modulus. The strain is equal to stress by Young's modulus, and stress is represented by sigma Young's modulus by capital E. Okay, so this is the strain by Hooke's law, and we know the strain in layer AB is y by r. So equating these two equations for strain, we will get the relation sigma by E is equal to y by r, and rearranging the terms, we will get sigma by y is E by r. So this is first part of bending equation. So the second part of bending equation is there, that also you will see. To derive the second part of this, consider any cross section of any shape. Actually, it may be rectangle, triangle, circle, whatever it may be. Okay, any irregular shape we'll take for explaining purpose. Okay, yeah, consider this any irregular shape. Let us consider. Okay, actually this may take any shape: rectangle, circular, okay, and in steel sections generally it takes I section or T section, anything. Okay, any cross section it may take any shape. So here in this cross section, let us consider an elementary strip at a distance y and of thickness dy. Okay, and let the area of this elementary strip be dA. Area of this elementary strip be dA. Okay, and we consider this layer at a distance y from neutral axis. Okay, at a distance y from neutral axis, where the stress is 0. At neutral axis, the stresses are 0. Okay, the area of the strip is delta A or dA. So the force acting on the strip, because the stresses, we have seen the expression for stress from the relation sigma by y is equal to E by r. Sigma is E by r into y. This relation we have seen first part of the bending equation. This is the relation that we have derived already. Sigma is equal to E by r into y, where sigma is stress at a distance y. Okay, from this, on any cross section, The variation of stress is linear because E by R is constant, Young's modulus is constant, and R is also constant. For the given loading, the radius of the bending curve remains constant. So the stress varies directly as distance from neutral area. So that is what is to be understood from this equation. Okay, from this part of equation, bending equation, what you have to understand is the stress remains proportional to the distance from neutral layer. What does this mean? The stress is maximum at maximum distance from neutral layer. Okay, that means towards compression side, as we have considered cantilever beam, bottom side is compression. Maximum compressive stress occurs at the bottommost fiber and maximum tensile stress occurs at the topmost fiber. Okay, this is maximum stress towards tension side and this is maximum stress towards compression side. Okay, and at any layer distant y from neutral axis, the stress is given by sigma by equation 1. Okay, so sigma is E by R into y. E by R is here constant, so sigma is proportional to y. E by R being constant, sigma remains directly proportional to the distance from neutral layer. Sigma is the stress. Okay, it is clear. So the top fibers are being subjected to tension and bottom fibers are subjected to compression. Okay, so the force, we are considering a layer here at a distance y of area delta A. So the force acting on this layer is the stress at that level multiplied by the area. So stress at the level y is sigma multiplied by area gives the force acting on this elementary strip. Okay, the force acting on the elementary strip is given as stress multiplied by the area of the strip. Yeah. That is what is shown here. Yeah. The force on the strip is delta sigma into area of the strip. Okay, this is clear. And sigma from this equation, bending equation, is given as E by R into y. Okay, so this force is the force acting on the strip, on the elementary strip. Okay, at a distance y from neutral layer. So force is given as sigma into delta A and sigma is given as E by R into y. Sigma is replaced by this. Okay, and now the moment of this force about neutral axis. This force will be acting on the cross section actually. This is the part of beam. Okay, at the neutral layer. This is the along the length delta x. Okay, this is neutral axis, neutral layer actually. Okay, so the force F will be acting on this. It is compressive or tensile. Okay, so if it is tensile, it will be acting away from this. It's clear. Yeah. This is the force acting. Okay, on the elementary strip of area delta A. It is clear. So now the moment of this force about neutral axis, the moment of this elementary force acting on the elementary strip is F into Y. The force is acting at a distance Y. So moment of this force about the neutral axis is force into distance. Okay, force into distance. So Fy is the moment of this elementary force about the neutral area, which is given as E by I integral y square delta. Okay. So now the total moment of the forces acting on the cross section. We have considered only one strip, elementary strip. Okay. We will have so many such elementary strips. So the total force is obtained by summing up all these elementary forces. Summing up all these elementary forces. Okay. Similarly, the total moment is obtained by summing up the moments due to elementary forces. Okay. So we have seen the force F as this one, and moment of the force, elementary force, is dm, which is given by this. Okay, this is the moment due to the elementary force acting on the strip. Understand? So the total moment is obtained by integrating this, by summing up all the forces from top to bottom, topmost fiber to bottommost fiber. Okay. Yeah, the summation is given by this symbol sigma E by R y square d. Okay, and we know that E by R is constant, so we can take that out of the symbol. So sigma y square delta A, E by R sigma y square delta A, that is the total moment about the neutral axis. Okay. So here the term sigma y square dA is called the second moment of area. First moment of area is y delta A. Second moment of area is y into y delta A. That is y square delta A. This is the second moment of area, which is also called as moment of inertia and is represented by symbol I. Second moment of area or the moment of inertia of the cross section of the beam. Okay. So, and is represented by I. So we can replace this sigma y square dA by I, which is nothing but the moment of inertia of the cross section. Okay. So M is now is E by R into I. E by R into I. So by rearranging this, you will get another relation. Okay. M by I is equal to E by R. And already we have got relation. One relation we have derived already as sigma by y is equal to E by R. Okay. This is equation 1 and this is equation 2. Okay. So from equations 1 and 2, by combining, we can combine these two because sigma by y is equal to E by R and M by I is also equal to E by R. So we can write the equation as M by I is equal to sigma by y is equal to E by R. So this is the final bending equation, okay, which is derived based on the assumptions what we made in the beginning. Okay. This is derived for the case of simple bending or pure bending. Okay. This is very important in solving the problems related to beams subjected to various types of loading. Okay. This is called the bending equation. Okay. M by I is equal to sigma by y is equal to E by R. Okay. from equation 2 on, equation 2 is this. This is equation 2. From equation 2, for the given cross section and loading, E is constant, I is constant, and bending moment is constant. Okay, bending moment is constant. I is, it is a geometric property of the section which is constant, and E is material property of the beam which is also a constant. So when these three are constants, then the radius of curvature also is constant. Okay, and which is given by the equation, R is equal to EI by M. That is M by I is equal to E by R. Okay, M by I is equal to E by R. This is the relation. Okay, so which gives radius as EI by R. Okay, thus for pure bending of uniform sections, beams will deflect into circular arcs. Why? How we can say the arc is circular is radius is constant. Okay, so for circular arcs only it is constant. Understand? So the radius of curvature is constant, means the beam bends into a circular arc under the action of the given loads, and is thus directly related to the value of the quantity EI. The radius of curvature depends on the value of the quantity EI, which is also known as flexural rigidity or stiffness. Flexural rigidity of the given cross section and material. Okay, because E is material property and I is geometric property, okay, of the cross section. So the radius of curvature depends on both the material as well as the shape of cross section of the beam. So the inspection of the shear force and bending moment diagrams shows that when the bending moment is maximum, the shear force is always 0. At the point of maximum bending moment, the shear force is 0. And it will also be shown later that bending produces by far the greatest magnitude of stress in all but a small minority of special loading cases, so that beams designed on the basis of the maximum bending moment using simple bending theory are generally more than adequate in strength at other points. So the cross section, the beam cross section is designed based on maximum bending moment. Okay, and that will be adequate in strength at other points also. Okay, once you design the cross section for maximum bending moment, that cross section will be adequate in resisting the bending moment at other points also. Okay, so when designing beams, the design is done based on the maximum bending moment which occurs in the beam for the given load cases. Okay, for example, in case of simply supported beam with central point load or with uniformly distributed load acting over the length, the bending moment is maximum at mid-span. So the beam section is designed for the maximum bending moment which occurs at mid-span. And in case of cantilever beams, For any loading, the maximum bending moment occurs at fixed end. So the cross section is designed for the maximum bending moment which occurs at fixed end in case of cantilevers. For any beam, for any loading, the bending moment is maximum at fixed end. Okay. But in case of simply supported, the position of maximum bending moment changes depending on the load. Okay. For symmetric loading, the bending moment will be maximum at mid span. For unsymmetric loading, it will be somewhere else that we should locate. Okay. The location and magnitude of maximum bending moment are to be determined first, and then design is made. Okay.
Like, share and subscribe. Hit the bell icon for more updates.